All right, so we're going to start chapter 9 today, which is dealing with polar coordinates and how those look in terms of getting to a location in space. And so what we're going to do is basically, we've looked at angles and we've looked at the unit circle. We've looked at x and y values in terms of coordinates and ordered pairs. We're going to kind of combine those ideas and talk about a different way to get to a point on a plane. So we're going to talk about all these different pieces where we have a polar coordinate system, what a pole is, the polar axis, our coordinates equation, and the graph. I'll just look through this. All right. So this first slide is really important to understand what we're talking about here. So if I have some point in space, the way that we've talked about it in our Cartesian or rectangular coordinates is I go over some amount and I go up some amount. We call that amount over x and the amount up y, and we have an ordered pair of x and y. And so if I had a point, if I was trying to graph the point 3, 4, right? The way that would look on my graph is I would go over 3, 1, 2, 3, and up 4, 1, 2, 3, 4, and I'd order that point 3, 4. Another way to get to that same point would be to go out some distance and then rotate some angle, and that would get me to that same location. And that idea of going out a distance and rotating an angle is going to be our polar coordinate. So instead of an over and up, so this one is not over and up, but it's going to be go out this distance r and rotate this angle theta. And as an ordered pair, we have an r and a theta. So if I was to take a polar point, let's say I go 45 degrees, what that would look like is I would go out 1, 2, 3, and then rotate that distance there, would come up 45 degrees. And you can see that if we wanted to, that's my distance of 3. We could try to convert back and forth between these. So to get to this point in terms of over and up, then we could use our trigonometry values to find the x component and the y component. And then we could convert back and forth. So we'll do that in a later part. But that's the key idea with this here is that instead of going horizontal and vertical, we go a specified distance and then rotate an angle. All right, so the way that we do this is our standard position, same as the unit circle. So I have I start on the horizontal axis is my polar axis. So what would usually be my positive x-axis is my polar axis. And then I rotate counterclockwise, counterclockwise, to get my angle. So, and I can see that I have co-terminal points. So unlike where rectangular, where I have one way to get to a point, for this one, I can have, I can go around multiple times. I can add 360 or 2 pi to get to the same spot. This one, a negative angle goes just like on a unit circle in the negative direction. So I have different ways I can get to the same location for polar coordinates. One thing that's a little bit tricky to remember is if I have a negative r value, what that's going to do is it's going to go in the opposite direction of what it normally would. So if I was to graph, let's say I have a polar coordinate, I'm going to go, let's say negative 3, 45 degrees, one we did before. So what we look at is, all right, 45 degrees and 3 before look like this, where that was 45. But since it's a negative 3, what happens is that gets flipped over this way. So we add 180 or pi radians, and it would go the other way. So we don't have the graph here at the top. What it would be in that quadrant, in that third quadrant there. So with our negatives, we need to be a little bit careful. We can see over here that you just you add or subtract 180 to get to those places. So there's different ways we can represent a point in terms of polar values. But again, remember it's a distance and an angle. We'll kind of keep track of it. All right. We also have the ability to get the distance between polar points. So we've seen this before with our distance formula for rectangular. It's a little bit different here with this, and we'll come back to this down the road. But really, it's just a fancy way to look at our law of cosines. We'll talk about that in a minute. All right. So let's look at an example. If I was trying to graph this, this is a polar coordinate. Again, this is my the first value is my distance, and then the second one is my angle. All right, so I have my graph. I have a terminal side of 200. I need to get that point, and then my graph looks like that. Again, that distance of 1 is important. The point that I'm graphing is still 1 point. And I have my polar axis is my horizontal axis that's set there. I was looking at another one, I have a -2. So again, this is going to go in the opposite direction. So it might be easiest to graph where is 3 pi over 2, right? And then go the other way from that to get my -2. So we look at that, that's going to be up, okay? So 3 pi over 2 was down here, or 270 degrees. But since the -2 makes me go in the other direction, a distance of 2 up. All right, and then this one is a negative angle, so I'm going to go out 4, and then I'm going to go down 90 degrees, because that's my direction, and that gives me that point. All right. So you're going to do on your sheet, you're going to try this one. You're going to go out a distance of 3, and then rotate 120 degrees, and sketch what that polar point coordinate looks like. Okay. We have, just like we have a coordinate grid that we're used to graphing on our standard graph paper with all the squares on it, we have a polar grid that we can look at too. And so a polar grid is going to look really similar to the unit circle. So we have a distance of 3, and I want to go out 5 pi over 6, and we'll put that on a polar grid. So the way that's going to look is, here's my polar grid. The way that we count out is, this is 0, a distance of 1, a distance of 2, a distance of 3, and then my standard angles. So this is out 3 at that rotation of 5 pi over 6. One difference between this and a unit circle is unit circle always had a distance of 1. This is going to count out by different values in terms of our length. So we can see this has a maximum distance of 4. That's the biggest that we could graph on this polar grid. Alright, so if we're graphing this on a polar grid, again, we can make it radians or degrees. It doesn't matter. We can go back and forth. We want to pay attention to the -2 that's out front here. That's going to go in the opposite direction of 240, and then we'll put our point on that. All right. So again, we find our value of -240. So that's -180, -240. And since it's the -2, it flips over, and I go out 2 on that point there. All right, you need to try this one on the provided polar grid that you have on your paper. Again, pay attention to the directions of the angles, and then if you have a negative r value, that's going to go in the opposite direction. Okay, since polar coordinates, we can add or subtract 180, and we have our negative values that will flip the sign. We have different ways that we can represent the same polar point. So if I'm trying to have given a polar point, so in this case we have point S, which is over here, I can see it's at a distance of 2, so a distance of 2 there, and then I have some angle that it's rotated. It looks like it's at 210 degrees as a positive. So I can see I have a positive, I have a negative, and then I could flip the signs to get my other angles. And that's basically what this goes through. So those are the first ones where I have my positives, right? So this is my positive values, and then making the same thing with a negative, right? So 210 and 30 are on the opposite sides from each other. So when I flip them over, I get onto the same point. And I can do the same thing with the others. So really what we're doing, we have our answer key in a second. We have those points. So if we're given a point that was over here, that's the point we're getting. We did our standard angle that way. We did our negative angle that way. And then we can add 360 to that. And that gets me around again. And then the negative angle. So if I have a negative angle, negative r value, let me get rid of some of these, right? If I give it a negative r value, so if r is negative, in this case it would be -2, right? That angle there is going to then make that flip onto that same point. So that's kind of what we did to get those ordered pairs that are at the bottom. Those are 4 points that are going to be the same location as the original. All right, so you need to do the same thing. You're given W over here in the corner. You need to find 4 coordinates that would have the same end result as W. So again, you're going to want to add and subtract 360 and use some negative r values to flip that point back onto where point W is. Okay, so now we're going to look at what a polar equation looks like. So we're used to the values in when we're looking at our Cartesian form. If I had x equals 5, right, I would have my coordinates and go over 1, 2, 3, 4, 5. Excuse me. And then I'd put a line there, going vertically at x equals 5. We could do something like y equals 2, and then I'd have 0, 1, 2, and then I'd have a line horizontally there. And we've done all sorts of stuff. This is what you're used to doing, right? If I was to do 2x plus 1 equals y, that's going to be a line. We've looked at x minus 1 squared equals y. That's a parabola. There's all the different ways that we've looked at the shapes that we can have with x and y. So we're going to have the same idea here with our polar corn, but it's going to behave a little bit differently. So when we look at r equals 2.5, r is a distance. So if we were to imagine I have some polar grid, and I go 1, 2, 3. One point that's 2.5 is right there. If I was to look at another one, I go up, 3, 2.5 is right there. If I was to go back, 2.5 is right there, and go down, 2.5 is right there. So those are points that are already 2.5 away from the origin. Now since I sketched this by hand, it's hard to see, but there's all these intermediary points in here as well, right? And what we're really sketching out, if we were to connect our dots, would be a circle. And that's going to be a circle when we graph it. Those are all the points that are 2.5 away from the origin. If we look at an actual scaled picture, it's going to look a lot better. So again, we get a circle that has a radius of 2.5. That becomes our graph. All right, if we're looking at an angle, so I have an angle value of 5 pi over 6. Anything along that ray, so starting off at 0, if I have my 0 as my angle, and then I have 5 pi over 6, so that's a 6 pi over 6 is pi. So 5 pi over 6 is anywhere in there. So any point that's along that line is going to have the correct angle. I don't care what r is. It can be any distance as long as it has that angle measured from our standard position. All right, so that graph is going to look like this. All right, within those values as we're looking at it. So that's my theta value of 5 pi over 6. All right, so you're going to use your guided practice to sketch a graph of theta equals 7 pi over 4. All right. Last piece is how do we find the distance between 2 points as we're given something in polar coordinates. And so it's easy to kind of think about what picture we're drawing here. So I'm going to look at this picture, and then I'm going to say that my origin is right there. I'm going to go out some distance. I'm going to say this is 5, and that was 20 degrees. And then I'm going to go out another distance. Let's say that's 3. And then this angle in here was, I don't know, 100 degrees. All right, I'm trying to find the distance between those 2 points. And what we've really drawn is a triangle. And if we look at it a little bit closer, what I have is 3, 5. I want to know that. And if I have this angle, then I can solve it. Well, I have that angle because it's going to be 20 is up to there and then 100 all the way around, so I can subtract those angles. 100 minus 20 is going to be 80. And so when I'm looking for this, when I have this relationship of side, angle, side, I'm going to use my law of cosines to solve for it. So I would get x squared equals 3 squared plus 5 squared minus 2 times 3 times 5. Cosine of the angle, in this case 80. And when I take the square root, we get r of x. All this big mess is that generalized. So you can use your law of cosines to determine what your distance is going to be. All right, and so we can just plug in those values, just like we have our rectangular distance formula. So our rectangular distance formula is the square root of x1 minus x2 squared plus y2 minus y1 squared. We can plug and chug through that. We can plug and chug through this distance formula to find the distance between points. So we'll look at an example of that real quick, where we give in 2 polar points and we want to know the distance between them. We apply our formula where we have r1, r2, theta 1, theta 2, and then we will plug it into the point. Okay? So we have our 2 values. Again, we can plug those pieces in to find the distance formula. So using the polar distance formula with my r1, r2, theta 1, theta 2 values, I plug them in, and then I get about 10.6 miles apart as the distance between those points. Alright, so you guys are going to, your last one here is to find the distance between those 2 points by using the polar distance formula.